Okay, I guess it's 3 o'clock. Let's get started. So, welcome back. This is the second part, logically, at least, of the two OAuth talks for today. So, the first one isn't the prerequisite for the second one, but they both kind of tell a story. So in the first one, we looked at the current security best practices, and for this one, we want to look more into the future, maybe, to see what else is out there. Some of the new techniques, some of the coming soon techniques to make OAuth more secure. Okay, so this time I'm better prepared. Actually, the slide deck is already uploaded to speakerdeck.com/thisprivilege. I just posted a link to the Slack channel as well, so you can get both slide decks right now. Oh yeah, and if you have any questions, at the end, we can do a Q&A with audio and video if you want to, or just audio. Or if you have any questions you want to queue at some point, just put them into the Slack channel, and I will get to them. Okay, cool. So for those who haven't been present for the first part, this talk and the material and so on is all part of a bigger effort around like a high security OAuth profile. So multiple industries have started taking the original OAuth and added additional specs to it, additional constraints or profiles as they call them, to make it more secure for for certain situations. So one is the most common or the most popular one definitely is the financial space. PSD2, the Payment Service Directive 2, is based on OAuth and OpenID Connect for doing payment initiation and things like that. So the FAPI working group at the OpenID Foundation created a more secure profile for OAuth and OpenID Connect. Now, I am myself involved in a similar work for the Norwegian HealthNet. Same idea, right? We are applying OAuth and OpenID Connect for the healthcare sector and added certain requirements because we need more security than what you can find in the plain specs. And similar things are happening in the States with the enterprise mission tailored OAuth profile. So yeah, hopefully we will be able to converge them. There is some work going on in this thing called FAPI2, which will be more like a general purpose high security OAuth thing, not tailored specifically to the financial API market. But the ideas are all the same, and I'm going to show you a couple of those things now. Okay, so that is these two talks I did are basically excerpts of a full day training I'm doing right now. But obviously that's too much content. Yeah, so basically I basically took that training material and turned it into a little bit more like a 60-minute chunk, I guess. So we're gonna start with basically what's the difference between OAuth 2.0 and 2.1. And then we're going to look at the next steps, basically the 3 big things, I guess, that are actionable today is improving front channel security, improving back channel security, and proof possession access tokens. Okay, so in my first talk this morning, I looked at the various what they call BCPs, best current practices. And there are a couple of them out there, the threat model, JSON Web Token, BCP, web apps, native apps, and so on. So the question is now, what is OAuth 2.1? So basically, you can think of OAuth 2.1 as basically all of these documents together become one new baseline OAuth specification called OAuth 2.1. And I mentioned these things earlier, but I want to basically point out the most important changes between 2.0 and 2.1. And that is that the implicit grant is gone, the password grant is gone. When you're using authorization code grant, you must use PXE to protect yourself against code injection and cross-site request forgery and other types of leakage attacks of the authorization code. There are strict requirements for how to validate the redirect URIs. We've seen many attacks around redirect URI validation, or flawed validation rather. So redirect URIs must be compared as exact strings, no variables or regular expressions, things like that, which it's very hard to validate URLs. Refresh tokens. We basically, since the implicit grant is gone, there are actually public clients that can legally, from a protocol point of view, use refresh tokens. I mean, that is, there are certain risks attached to that. So there's a pretty simple statement here. If you are a confidential client, you must use a client secret to sender constrain refresh tokens. If you are a public client and want to use them, then you should use refresh token rotation, meaning you should only use the refresh token once, and then the next time you get a new refresh token. This allows you to detect replay attacks, and this also allows you to act on these replay attacks by, for example, revoking the refresh token automatically if you think that is malicious, right? And the last thing is a small one, but basically OAuth, or rather RFC 6750, allowed to send bearer tokens over a query string. That is not allowed anymore. You must either use the authorization header or the post body. Okay, so that's our starting point. And now we want to look at additional specifications that sit on top of OAuth to improve the security. So the first part, the first complex will be around front channel improvement. So, basically a typical OAuth flow for an interactive application consists of two channels. One we call the front channel, which is over the browser, where the interactive UI happens. And then this returns an authorization code, and then the back channel takes over, where the client opens a back channel communication to turn that code into tokens. So it turns out the front channel is the most vulnerable one because it happens in the browser, it happens on the user's machine, right? And that's why, like modifying URLs or even, leaking data from there is a concern, okay? So let me introduce you to Ra, Char, and Pa, which are not a reggae band or something. There are three independent specs that target in hardening the front channel in OAuth. So let's start with Ra. So Ra stands for Rich Authorization Request. And the reason it exists is that more and more OAuth protocols or specifications have the need of transmitting structured data from the client to the authorization server. For example, in the banking industry, where you want to make the user consent to a banking transaction, basically, do you allow sending 50 euros to the pizza shop, things like that. This is around transaction IDs. Or there's another spec in the healthcare world, which is called Smart on Fire, that, for example, says, do you want to allow this client to read the electronic health record of patient 5, okay, but only patient 5. Even if the user, the doctor, has access to more patients, we want to only allow that client to get access to this single patient, right? And since OAuth itself does not have a concept of structured scopes, many people just came up with their own little format. For example, here, something like scope colon parameter, right? Transaction colon ID or patient colon something, okay? So this is, I mean, the original OAuth spec does not mandate any format here, but most implementations just say, okay, there are some scopes and there is no features built in for parameterizing those scopes. So I can show you, for example, in the latest version of IdentityServer, how we implemented this requirement, right? So basically here is a scope called transaction. And now the idea is that a client can now basically ask for a scope called transaction colon 123. This scope is not registered, right? The only thing you want to register with that scope is the base name, and then at runtime, that thing that comes after the dot should become the variable part, if you like. So we have introduced a new feature in IdentityServer, for example, that is called a resource validator. And here you can basically at runtime look at the scope values and see does the scope have a format that you know, right? Then it allows you basically to pass that scope name and then take it apart. Basically, that's the name of the scope, and that is the variable part, and then you have the variable available to the rest of the pipeline. Okay, so actually, let's run this, and then when you have a client then that asks for such a scope, let's see here. So here's a client that asked for a scope transaction : 123. Then basically at runtime we know, okay, the scope is actually transaction, but there's a variable part to that, yeah. And then you can basically, grant such a scope or even derive other claims from that scope. But to be honest with you, that is really just a workaround for the fact that OAuth itself does not have the concept of structured scopes, right? I mean, this works for many situations, but it's not what rich authorization requests are. They go much further. So rich authorization requests introduce a new parameter called authorization detail, and that replaces the scope parameter, right? So maybe you want to say, like, allow the client to make a payment of 45 euros, or allow the client to read a folder and write a file, things like that. Yeah. Instead of coming up now with your own arbitrary complex structured scope string, the rich authorization requests goes basically further in the way of that. Basically, you are sending a structured object along with the authorized request, which has a schema, so it's strongly typed. Yeah, it has the concept of the data type you want to access, and maybe even an identifier for a specific data type, right? So maybe you want to say, like, hey, allow this company to print picture number 1, but only number 1. They should not be able to access picture 2, 3, and 5 on your Google Drive or whatever. And as I said, instead of like coming up with your own custom data format, they are basically saying, yeah, just use an object so we can describe this properly, right? That is another example, yeah, of another schema, which is basically modeling file system permissions, right? So, like have read access to this file, have write access to this file, for example. And then the idea is, as I said, that this thing replaces the scope parameter and basically can be used wherever else you would use the scope parameter, okay? So for example, that is an example of the authorized request. You have your normal parameters here, like response type and so on. And then you have this thing called authorization details here, and that is the encoded JSON object that is the structured scope, okay? And that obviously gives you far more expressiveness than, like having a little string that now, becomes ultimately complex. Also, by introducing a schema, this allows authorization servers to look at the schema and then present a consent screen that is optimized for that situation, instead of trying to come up with a general consent screen that can show all kinds of different things. You can say, oh, that's a payment initiation. Let's show them a consent screen that like says, okay, who is the initiator? What's the target account? What's the amount? What's the currency? All these things, basically. Okay, and then if the and same as with scopes, if the user consents the client is allowed to ask for that scope of access, the authorization detail will get embedded into the access token. This access token will flow to the API, and the API can then say, okay, this in this case, subject ID 123 authorized client 456 to transfer 45 euros from bank account A to bank account B. Okay, so that's rich authorization requests. Now you might ask yourself, this probably is a bit of a sensitive string, right? I mean, if you could modify that string we could change maybe bank account numbers and amounts and so on, and maybe there is no consent, or consent, the user, consents by accident, things like that. So it would be nice to be able to protect the data. I mean, generally speaking, it would be nice in OAuth that to protect the whole authorization request, right? Because as I said, there is potential for misuse here. And that is another spec that is almost done. It's like in the last stages of being finalized. It's called the CHOT, Secured Authorization Requests spec, or CHAR, as many say. And the idea is really, as I just said, instead of passing unprotected query string name value pairs over the authorized request, you sign the query string. Okay, and the easiest way to sign a piece of data these days is basically by wrapping it into a JSON object, signing that JSON object, and that is called a JSON Web Token. Yeah, which means an attacker could not change the values of the parameters after the chart has been created. You can, which is pretty cool, authenticate the client already on the front channel and don't have to wait until the back channel. And if confidentiality is a thing, then you can also encrypt these tokens if you want, and then basically avoid a whole class of attacks that deal with leaking data, rewriting URLs, or mix-up attacks, things like this. So the way this works is basically, imagine that is your authorization request, and then basically instead of transmitting this to the token service, you are transmitting this. Okay, so the only two parameters that are left here is the client ID, which is mandatory still, and then everything else is replaced with this parameter called request, and this here is a JSON Web Token. Okay, so if we look inside the JSON Web Token, you see that's how it looks like. It basically has the things that used to be on the query string is now key value pairs inside the JSON Web Token. And that is pretty cool. Yeah, as I said, it's not hard to implement this. It gives you nice security properties. Yeah, and again, if you want to see an example of how that's implemented, so in IdentityServer, all you need to do basically is you associate an asymmetric key with the client, and we'll see later on when we talk about client authentication that the same key can be reused also for the back channel authentication bit, and then that's it, right? So once you have that key associated, in this case, IdentityServer is able to validate the incoming CHOT token, turn it back into an authorized request, and just use it. And if you even want to force the client to use this new technique because it's more secure, then you can say require request object, and then for this particular client, IdentityServer will not accept anymore a non-signed authorized request. Okay, so I can show you that. Basically, that is running already. So here's the config. Let's have a look at my char client. It's here. That's pretty much what you just saw on the slides. Here's that client. Here's the JSON web key. There is an RSA public key. I require the usage of signatures, and the rest is just normal business. And when I run this, here's an MDC client. And when I add the, open the network trace and say, log in, you can see that basically here's my authorized request going from the MVC client to the server. And you can see that basically all parameters have been replaced by this one request parameter. The only parameter that's present is the client ID. And that's an unfortunate problem in MVC. I cannot remove the redirect URI because MVC needs that internally, but it's being ignored because everything that's inside the chart takes precedence over what's outside the chart. And since the redirect URI is inside the chart, it will be overwritten basically by, or even to be honest, even if there would be a mismatch between the two, what's inside and what's outside, in the case of IdentityServer, we would actually throw an exception. Okay, so that's cool. That makes your authorized request much more secure. So I can log in just as normal, everything else stays the same. If you are interested in how that works in ASP.NET Core, it's actually pretty cool that it's possible to do that without Microsoft, when they created the feature, didn't know about that this will be a thing someday. Yeah. Let's get rid of that. You basically see that you can, in the OpenID Connect handler in ASP.NET Core, you can plug into the various events that are getting emitted. Yeah, and the one that we are particularly interested in is the event that gets fired before we go to the authorization server. Yeah, and when we go to our OIDC events thing, you can see that there's an event called redirect to identity provider. And then you see what I'm basically doing is I'm taking the protocol message from the context, I'm signing it. That's what this is doing. That gives me this JSON web object, JSON web token that contains the parameters. Then I'm removing all the parameters from the request. I set back client ID, I have to set back redirect URI, and I'm adding the rest as this additional parameter. And that's all you have to do. And then you're running on signed authorized requests, which is pretty cool. Okay, so that's char. One concern with char, right? So one leads to the other. If we have a look back here, is that this becomes a pretty long URL. Okay, so if you imagine now your char contains a RA, right, the authorization details, this JSON web token will get bigger and bigger, and this might be a problem for certain browsers, especially on mobile devices, might be also a performance thing. Maybe the client does not have the crypto libraries to create that JSON web token. I mean, in the .NET space, it's all pretty easy, but what in other places. So the next spec, think of it as a complementary spec on top of char, is called PAR, which stands for pushed authorization requests. And the idea is that instead that the client creates the JWT and sends it over the front channel, basically what the client is doing, it first opens a back channel communication and pushes all those parameters it wants to use over a back channel, which means we can authenticate the client again even before they open the front channel. Yeah, and basically, and you see basically what happens here is that what the client is doing, it pushes all those parameters, and then the authorization server will store these parameters for the client for a limited amount of time, and it will return back to the client a reference to these pushed parameters, which they call a request URI. And you see that they say like, and this will be valid for 90 seconds. So that's basically before even the client opens the front channel, it first does the back channel communication. And if it's a confidential client, we can combine that with client authentication, right? You could even also push a request object, basically not just plain text variables, but a JSON web token, for example, if you need the signature for non-repudiation purposes in banking, for example, or healthcare. And then when the client has this thing back, all the client needs to transmit over the front channel is pretty much only the client ID and this new parameter called request URI, which then points to this previously pushed authorization parameters. And that's pretty neat, I think, right? Because that makes the URL super short. There's nothing anymore that can be manipulated. This is a random thing with a lot of entropy that no one can play around with. And that is probably even easier to implement than creating the JSON web token on the client side. Okay, so that is from my point of view the three big new things coming for the front channel. Rich authorization requests will take a while until this will be finalized. That's a pretty new spec. Char, the JSON web token authorization requests, that one is pretty much done. And PAR is so simple as a spec. Basically, the authorization server creates this endpoint to receive parameters, gives back an identifier. I'm expecting this to be available as a finalized spec pretty soon. It's definitely something we are working on for the next version of IdentityServer. Okay, so just to summarize that, RA is a replacement for the scope parameter. Char allows for signed and authenticated authorization requests, and if needed, encrypted. Also, another thing I didn't mention explicitly is if using the char approach, you can also transmit additional data over the front channel. And since it's in that signed JSON Web Token, that data becomes trusted from an authorization server point of view. And that might be interesting if the client has to transmit additional data. And PAR really is a refinement of char, if you like, which provides a dedicated endpoint to push the authorization request data up front, and then it can be used over the front channel. Okay, so that's the front channel improvement, if you like. The back channel is basically then the thing that takes over once the authorization code has been transmitted back to the client, or if you are in a non-interactive flow like client credential, for example, whenever the client basically wants to request a token, right? So if it's a confidential client, which, you know, for most cases it is, the client has to authenticate with the authorization server. And the most prevalent authentication method these days is shared secrets, basically, right? I mean, I mentioned it this morning. It is easy to get started with, right? You just have a string, you share that string, and yeah, it's working, yeah? For everyone who deployed this authentication method at a larger scale knows that there are some challenges, right? I mean, you need to store them somewhere. On the server side, you want to store them hashed. On the client side, you need them back in its original form, so you can't hash them. The configuration system must distribute these things somehow securely. Yeah, so long story short, shared secrets are a bit of a pain, because also, you know, how good is the secret when it's shared? Yeah. Generally speaking, the recommendation is to get away from shared secrets. Also, you know, like one thing that is a big concern is that shared secrets are getting transmitted over the network. Yeah. So, you know, I just had a customer last week where, you know, they have deployed software in the company, or a hospital in their case, and the services they want to access are in the cloud, right? So even if they can protect those secrets effectively on the machines because they control the hardware, the secrets travel over the network, right? And since they are not controlling the network infrastructure, they are, you know, they go over reverse proxies and so on. You know, that those secrets are exposed. Yeah, it would be nice to have something more robust, and that basically is secrets based on asymmetric keys. Okay, so the idea is simple. Instead of having a shared secret or a symmetric key, on both ends, the authorization server only has the public key. The client has the private key, which also means the authorization server does not have to store that secret in any special protection mode, right? Because it's not a secret; it's a public key. The client, yes, the client needs to store that secret securely. There's no way around that, regardless how you do it. Yeah. And then, because you can then prove knowledge of that private key by using a signature instead of transmitting the key itself, that secret is never exposed over the wire. So the whole network leakage, eavesdropping thing concern is not existing. There are two ways of you know, leveraging. Well, there are many ways, but there are two official ways of leveraging asymmetric keys for client authentication. One is called private key chart, and it's more like an application level solution where you are writing explicitly code to sign something and then use that as an authenticator. The other one is using good old mutual TLS, you know, like X509 certificates, where the transport channel takes care of the crypto. and thus, allows that the client proves he knows a certain secret to the server and vice versa. And you can combine both methods, which we'll see is an interesting technique later in the talk. Okay, let's have a look at private key JWT. The private key JWT, basically the idea is instead of sending the shared secret over the wire, what the client is doing, similar to the idea with char, like the signed authorized requests, the client creates a JSON Web Token and signs it with the private key. Okay, and then this is basically used as a replacement for the secret, because now the client has a piece of data that proves that he knows the client key, the private key, sorry. What's inside of that JSON Web Token? Well, there are a couple of claims that must be in there, like the issuer claim and the subject ID claim. They contain the client ID of the OAuth client. The audience claim must point to the token endpoint of the authorization server. JTI is a unique identifier, like a GUID, for example, that allows us to do replay detection, which is another nice feature of this authentication method, since we can detect replayed requests, because the JTI, you would see it twice, right? And you see, oh, so somebody used that token twice. Expiration, well, which is basically trimming down how long your replay cache must be. And then issued ad tells you how old the token is or when it was issued. Yeah. So basically, the job of the client is now to basically create such a JSON Web Token, and instead of transmitting the client ID client secret, the client basically sets a client assertion, which is the JSON Web Token, and then there's an official client assertion type. Okay. So all the code that's necessary for doing that is on the slides, but I think it's more exciting to show it to you in a real example. So again, let's have a look at the server configuration first. How would you configure such a client? Well, and guess what? It is exactly the same as you would do with the signed authorized request. In other words, you can use the same credential now to do authentication on both the front and the back channel. Okay. There's another client which has a little bit more options here. There's this guy. So, in IdentityServer, generally speaking, you can leverage this using, and I mentioned it earlier, X509 certificates, yeah, that is just an X509 cert as its base 64 form, or a JSON Web Key. And the JSON Web Key is a more general purpose data structure, because you can format any type of key with that. I mean, you could even use symmetric keys if you want to, but I wouldn't recommend it. Yeah, I would say stick with an asymmetric one, use RSA or elliptic curves. Okay, and that's it basically from an identifier point of view. Almost, at least, you plug in the correct secret validator and parser type in here, and then basically what happens is when you go to the OpenID Connect provider and you go to the discovery document, you will see that it has an authentication method that it supports. Where is it? Grant types, response types, response. Oh yeah, token endpoint authentication method, and it says private key JWT. That tells you, okay, this is supported by the OpenID Connect provider. So now that's the server setup, and now let's have a look at the private key JWT client side. So that's a console sample here, and the idea is pretty simple. You are creating the JSON Web Token. That happens, create here. So you see that basically here we are creating a JSON Web Token using the private key. Here are the claims that must be in there: the client ID, the audience, the JSON Web Token ID, the issuance time, the not before, like when is the token valid and when does it expire, right? That creates a string, yeah, which is basically your credential, yeah? And then you can request the token, right? And instead of passing in a client ID and a client secret, we are passing in a client assertion, as they call it. The type of the assertion is a constant, which comes from the spec, and that is the JSON Web Token we just created. Okay, And that returns basically an access token. And from that point on, you just call your APIs as normal. Okay, so when I run this, here's my private key JWT console. So basically you see here, that's the token response coming from the server. And it's just a normal token, just that for accessing that token, we haven't used a shared secret. It's now using a private public key pair, and that's it. Okay. Oh yeah, and the same, I guess I should show you the same for MDC. That is also always a good exercise to see how that would work in a real application. So private key JWT, here's my MDC guy. And I'm basically using the same technique as before. I'm hooking in those events, yeah, the OIDC events. And when we have a look at that, you can see that Microsoft kind of prepared for the scenario where you don't use a shared secret. They don't have a built-in implementation for doing, like all of the token creation and so on. But when you are basically hooking this event here, authorization code received, that is happening after you receive the authorization code, but before you redeem the code and turn it back into a token. You see that basically on this context, they are passing in here that there's a token endpoint request. Then you can set the client assertion type and the client assertion, and then this is used instead of a client secret. Okay, so actually when we look at my startup here, you can see that I haven't even, there is no client secret configured here because this is the JSON Web Token that gets generated on the fly. Okay, so that is cool as well. Oh yeah, and again, I should mention, since we are creating the JSON Web Token, we can add more content to it if we want to, right? Additional claims that would flow to the authorization server, and maybe you want to drive some custom logic on that, on the fact that you have additional data being transported from the client to the token endpoint. Okay, so here's all the code I just showed you. We don't need to do that again. Cool. So to be honest with you, that's what I would do. Yeah, I would go away from shared secrets, right? Deploy a public client key pair instead for my clients, and then switch both on the front channel and on the back channel to signed, artifacts, right? On the front channel, sign my authorized request. On the back channel, use the private key JWT instead of my client secret. You can use the same key material, yeah, and that's great. And that basically gives you better security. Now, that is only about the client to token service communication. Another thing that is a real security concern is what happens if you're leaking the access token, right? Now we used all of these new bells and whistles to make the token request more secure. But what if you are leaking or the token, right? So once the attacker has stolen a token, it doesn't matter anymore how secure your authentication method was, the token is gone and it can be used, right? That is the whole crux of the bearer token concept in OAuth, that there is no binding from the token to the client that requested the token in the first place. So if the client is leaking the token, it can be used by an attacker to impersonate the client or impersonate the user, okay? So the opposite of bearer tokens is called proof of possession tokens, right? Where basically you find a way to cryptographically bind the access token to the owner, to the client. And if an attacker would now be able to steal that access token, the attacker could not use the access token because it's missing the last secret, so to speak, to prove that he owns the token as well, okay? That is, to be honest with you, not very easy to accomplish. I mean, there have been many attempts to solve the problem. Either you are introducing heavy crypto at the application level, because basically you need to somehow bind the token to the client, and the client now needs to prove to the API that he knows the private key by signing the HTTP request, for example. This has been proven to work, but has never really gotten any traction because it's pretty complicated, and also there are some unsolved problems with application level token binding, like for example streaming, right? I mean, the whole signature thing requires you to have a chunk of data to be able to run a hash over that, but a stream of data, you know, that's harder to do. Many people thought maybe the transport layer can save us, and there was a spec in the working called token binding, but that never got really a lot of traction. So we were basically back to square one and thought like, how can we introduce this proof of possession semantics? Yeah? So just to summarize this is the real problem, right? You are sending a token from the client to the API, and attacker is able to steal that token somehow. Yeah, the attacker can replay the token and impersonate the client. So after many years of trying to find solutions, we are basically coming back to a technology which has been around for many years, and it's called mutual TLS. Yeah, or some people call it client certificates. Yeah, for TLS. So you know that normally when you do HTTPS, yeah, what you're doing is you are authenticating the server, right? So you know, many people think TLS is all about encryption and stuff. Well, it does encryption as well, but first and foremost, the biggest benefit of TLS is that it authenticates the server, right? Because you know, before you send confidential stuff to the server, you want to know you're in the right place. Yeah? There's an extension to TLS for client-side authentication, which is not used that often because historically there have been problems with that, and when people hear mutual TLS, they think of PKI and CAs and so on. But to be honest with you, there's a renaissance around mutual TLS. It's gotten easier to use, and maybe you don't need all that PKI stuff, as I'll show you in a second, right? So if you employ certificates on both ends of the TLS tunnel, you can authenticate both sides. Okay, and in essence, what that means is that both sides can prove they know a certain private. Well, both sides can prove they know a secret. Okay, and once both sides are happy with the other one saying, I know the secret, and that's how I prove it to you, and that's very complicated. Yeah, in reality, we can be very sure that, you know, we know the identity of each other. Now, with that level of approval, what the token service can do actually is embed inside the access token an identifier that represents the secret that the client has proven to know during the token request. Okay, so in other words, only this particular client here can prove that he knows a secret, and the secret identifier is what we call a thumbprint, which is technically the hash of the public portion of the X509 certificate, in this case with SHA-256, so that's why it's called X5T-S256. And the special claim for that is called the CNF claim. It's the confirmation claim. So in other words, this CNF claim binds the access token to the client. Okay, cool. So now, how does that work? I mean, how do we make it work? So what about this? What if, you know, a client, when it starts up, just creates a public-private key pair, an X509 certificate, basically, and then uses that X509 certificate to basically start the TLS handshake with the token service, right? Now, the token service would embed that thumbprint in there, and then the client would use the same certificate to open the TLS channel to the API. Now, the API, once the TLS handshake is done successfully, he will also see on the TLS channel this value here. So all the client now needs to do is compare the value he got from the TLS channel with the value that's inside the access token. And if they match, he knows that this is actually the client that asked for the token in the first place, or in other words, the client proved possession. Okay? Sounds complicated? Yeah, well, security is hard, right? But it's not undoable, right? So the good news is starting with .NET Core 2 point something, we can actually in code create X509 certificates on the fly. Okay, that's all the code you need, and there are some magic things in there that don't, whatever, it works. Yeah. What this creates does is it generates me an X509 certificate on the fly that I can use for opening a TLS channel. And for opening the TLS channel, all you need to do is you assign that certificate that we just created to the handler that you use to open your HTTP client. Okay, and then basically all you need to do is request the token, create the HTTP client, assign the certificate to it, and then do your token request. Okay, and from that point on, that certificate will be used to authenticate, in quote unquote, the client, and that can be used then for the by the token server to embed this thumbprint into the access token. Yeah, this certificate is not used really for authentication, right? It's just an additional secret that the client provides that allows the token service to bind the token to that secret. Yeah, and as long as the attacker does not know that additional secret, it cannot use the token and since the secret never went over the wire, just the public key part, that's how that works. Okay, so let me just show you first how this works in action, and then we can have a look at some considerations around that. Okay, so here's my, let's see, where is my MTLS guy? Okay, so here you see, here we are generating the certificate, and then we are requesting the token, and then, I will just output the token on the screen. So let's do that. And then you'll see that the token will contain this thumbprint. Okay, so here you see, that's the resulting access token, and here's an additional claim now, and that's exactly the thumbprint. Okay, so now basically what I need to do is in my API, I've written an additional middleware, and what this middleware is doing basically is it does exactly what I mentioned earlier. It gets the client certificate from the transport channel. It gets the thumbprint for that certificate, which is basically the base64 URL version of the SHA-256 hash of the certificate, right? And then it extracts the value of this X5T claim from the JSON Web Token. And if they match, all is good. If they don't match, then, well, we reject the request. And that means that the client has not proven to know that secret. Okay, so that's how that works. Now, setting up mutual TLS is a bit more involved. Yeah, I totally have to admit that. Yeah, but you only have to do that once. Yeah. So first of all, you have to think about basically it doesn't work really well to share both non-mutual TLS and mutual TLS endpoints on the same connection, right? So IIS does that historically with dedicated paths here. That is not going forward with HTTP2 and beyond. So basically what you have to do is separate them maybe on the domain name. Yeah, so it could be a separate domain name, could be a subdomain, for example. Yeah, that's my preferred version. Yeah, putting them on the subdomain. And regardless which method you're choosing, when you look at the metadata of your token service, there will be a new element called MTLS Endpoint Aliases. And that basically says, okay, if you're looking for the MTLS version of the token endpoint, that is the one to look for and not the other one. Okay. So once you have that, you have to deploy this somewhere or host it. I had a look at a couple of web server choices. And IIS, as I said, does only path-based. Azure does path-based as well, but in a weird way. Kestrel does not support the isolation out of the box. They're working on that for the next version. The one that I had the best results with is Nginx, to be honest. That is super flexible, how to host your endpoints and TLS settings and so on. And I'm pretty sure there are other options here as well. But if you're using Nginx, basically the idea is pretty simple. You host your application here on your normal domain, right? And that's all of the headers you're passing through. So when a request comes in, you are forwarding that to the internal server, your local host 5000, whatever. And then you're setting up a separate server here, which is the subdomain, which does MTLS. And then you said, okay, I want MTLS here. And then you can, have some options about, do I require PKI or not? I didn't require that. And then basically you're telling Nginx to forward the TLS certificate as a header to ASP.NET Core. Okay. And then on the ASP.NET Core side, you need to turn that header back into an X509 certificate. There's a built-in middleware for that. It's the certificate forwarding middleware. And you basically have to tell that middleware how to turn that header back into an X509 certificate. In the case of Nginx, you basically URL decode the header, and that basically is the byte array, and that is your X509 cert. So that's easy enough. And then you wire up support for X509. And again, this is all built in. It's nothing that I added to ASP.NET Core. It is all built in since version 3.0. And then the last thing I did was I actually enabled mutual TLS on IdentityServer, and that is how I validate that and then can embed the CNF claim into the access token. Okay, that is how I did it at the API. I showed you that already. That's my validation middleware. So just to prove that it works, let's actually run the API as well. Okay, so here's my API. And here is my client. So that is now my token request. And when I hit enter, I call my API. So the API was happy with my token, which means that it was able to match the thumbprint. Okay. Oh yeah, very last thing maybe to show you how that works in ASP.NET Core as a client. Yeah. So there is an MTLS MVC app. So that is a bit of a funny story. So Microsoft has half of the support we need. Yeah. So first of all, I'm making use of the fact that in ASP.NET Core, in the OpenID Connect handler, you can replace the backchannel HTTP client. So basically, all I'm doing here really is I'm replacing the HTTP client, and I'm inserting my certificate. Okay. The other complication you will run into is that they don't know anything about these MTLS endpoint aliases. Yeah. So you have to tell them to use different endpoints when they are opening the backchannel. Yeah. I haven't found a good way of doing that besides replacing their complete OpenID Connect discovery document plumbing, yeah, which sounds worse than it is. Basically, what I was able to do is I wrote my own IE configuration manager. I'm using internally the standard one they have, yeah. And then basically, whenever they want to get my configuration, I'm first calling the built-in configuration manager, and then I'm fixing up on the fly the endpoint URLs for the token endpoint, and in this case also for the revocation endpoint. Then from an ASP.NET Core point of view, they don't know about this. They're using MTLS, and it works. Okay, so you can tell that ASP.NET Core was not written for many of these advanced features in mind, but I think it's a good sign that the extensibility model that they have allows you to do all the things, okay, without, you know, major surgery, I guess, to the framework. Okay. So that's it. Yeah. Obviously, there's more to learn here, but these are the, you know, my main key takeaways. Yeah. Secure the front channel. Use asymmetric keys. Yeah. Use the private key JWT mechanism for the back channel, and then you can, if you are interested in this proof of possession feature, you can layer on top TLS client certificates. Yeah. You don't need a CA for that. You don't need a PKI for that. You can just generate them yourself. The client doesn't even need to be a confidential client. Yeah, I mean, imagine. I think where this is a really compelling feature is for native mobile applications, right? Because these are the types of applications which are typically exposed to untrusted networks. Yeah, and if this you know, your mobile app generates this session certificate when it asks for the token, then it can, you know, use the access token, and even if the token gets leaked over, you know, maybe this access point at the airport called free Wi-Fi is not as secure as you think, right? So even if that token gets leaked over there, the attacker cannot use it because it is missing the private key of the session certificate. So I think that is, without too much effort, a way to tremendously increase the security of your OAuth deployment. Okay, so that's it from my point of view. If you have any questions, please speak up now with audio. Otherwise, put them into the Slack channel and I will get to them, or maybe I will get to them right now. So there's one question: do you generate the MTLS certificate for each client, for each request, or something else? Basically, it is for each token request. Well, it depends, right? So it's a so-called session certificate, right? And you define what that means, what a session is for you. Maybe it is per application startup. Maybe you do it per token request, right? The point is you have to use the same TLS certificate for both the request to the token service and the request to the API. So they logically belong together, right? But besides that, you know, you can mix and match any way you want. The next question is, how about load balance clients? Do they need to synchronize MTLS sets? No, they don't, right? That's the nice thing about it, yeah. It's just an additional key that you are transmitting alongside the token request. There is no registration for that necessarily, nothing. It's just, imagine you're doing a normal token request, but provide an additional secret that the token service can bind to the token. That's about it.